start. I'm very pleased to introduce you Dan Thomsen from Tresys Technology. Dan has been working, is very well known in the security area. He has been working on security for more than 17 years. And he kind of was one of the first person to propose the notion of type enforcement.
My company, I was there.
His company.
I was there.
Yeah, he was there. And actually he has a lot of experience in working on various research topics. And what I really, really knew about his work was more related to tools for specification of access control and security policy. So I'm also glad to say that this year he is the program chair for the AXAC conference, which is Application Security Conference, very well-known conference.
Right, and I have flyers here for that, actually, if you're interested. Right.
So I leave him to his presentation.
All right, so what I'm going to be talking about today is I've been doing analyzing security policies, and that's what I've been doing for the last year. I've been at Tresys off and on, and so I was going to talk about that and some of the engineering choices you have to make when you're analyzing security policies. It's really a whole new area, and it sort of ties into software engineering. Security policy engineering is sort of a new area, and I'm going to talk specifically about what we're doing for type enforcement. So basically, I'll talk a little bit about the security environment where I'm analyzing the policy and trying to improve security. And then I'll go into some of the patterns that we use to improve security, how we modify the policy or modify the software to improve security, some of the tools you have in your bag to sort of improve security. And then I'll talk about the actual analysis. What do we look for when we're looking at a policy, trying to make the policy better? What are we trying to optimize when we make the policy? And then I'll talk specifically about the information flow analysis that we're doing as we watch data move around. Now, to some of you, what the kind of analysis I'm doing, the in-depth analysis, might seem really odd. And so I wanted to give a couple slides on why we're doing this the way we're doing it. Why, as you'll see later on, it basically becomes a big graph problem we're trying to optimize in a very particular way. Why are you trying to optimize the graph that way? It doesn't make sense. There are other factors that you might want to do. Well, it really gets down to a matter of economics. At each stage in the process development for software, we're finding that economics are a huge factor. Well, there's also a similar set of factors that apply to computer security that make it quite difficult. So some of the questions arise, what operating system are you using? That determines what kind of security controls you can put in place. And then it determines how much granularity of control you have and what kind of tricks you can have in your bag for improving the security of the system. How much analysis can you afford? When I was at Secure Computing years ago, I worked on a high assurance platform where we had 10 mathematicians working about proving aspects about the system. Very expensive. So if you have that kind of level, you can do a lot more analysis. Then the bottom line comes down to how much does it cost if you get compromised? So and the bottom line, this last bullet here is the really important point. If you say, I'm going to do ivory tower security, and I'm going to spend all the money I have, and I'm going to build the greatest system, the most secure system ever, but you never get to release the system because you're spending so much time on it, people will march forward and they will use whatever existing technology is out there, and they will make do with much less security. So the idea is sort of here that you'll see me as I go forward is get the most security out there as fast as you can and then incrementally improve it. Just to characterize it a bit more, commercial versus government. In a commercial arena, what they'll often do is they'll buy insurance. If I get a compromise or my system fails, that's traditionally how they handle it as insurance. I'll pay some a little bit of money now, and if I get a really catastrophic failure, the insurance company will cover me. They'll also do it with software license agreements, right? If the software breaks, it's not our fault. And then, of course, the other problem is they have a financial goal, right? Their whole job of a company is to make money. And so if they have a compromise, it might cost them X amount of money. So they can look at that and they say, okay, it's going to cost us Y to fix it. If we get compromised, it's going to take X. They balance it out and they make a decision. In the government arena where I'm working and analyzing these policies, those financial equations don't really work because the costs are too high. Maybe you're talking about loss of intelligence data, or troop movements. I mean, so you're talking about loss of human life or loss of, strategic advantage. They're huge. You really can't put financial factors on that. So that gives you a little background of why we're doing all this complex analysis. The target mechanism here we're going for is security enhanced Linux. This is an operating system project that came out of NSA. It's one of the few projects that comes out of NSA that has an open outreach where they're trying to get people to use it. Normally they're very hush-hush about whatever they do. So, but they took Linux, a mainstream operating system. They have security hooks now, and so they put out another layer in the kernel then where they basically have these security operating hooks for doing type enforcement. And it has other security hooks as well, like a multi-level secure policy and other things. But what we're interested in today is a type enforcement, and I'll talk about that in a minute. But the important thing here is it's a mandatory security policy. The kind of traditional access controls you find in a Unix operating system are discretionary, meaning the users set them up, and the system administrator sets them up, and maybe he puts some guidelines on you. But as I'll show later on, there's some problems with those types of policies. So you really need to really improve the security of your system. You need to have a mandatory security policy. As I said, a lot of this gets back to economics. SE Linux is freely available. Now, the analysis you'll see is expensive, that what I'm going to do, but at least you've got a free mechanism, and you've got a chance of getting people to buy in and start using this policy to improve the quality of systems. Now, Linux is not a high assurance platform, and if you look around, there are no high assurance platforms because they're very expensive and hard to build. And I'm talking about the common criteria where they evaluate systems, and they have various levels like EAL1, EAL2, EAL4. Now, Linux itself has been evaluated at EAL2 and 3 for different applications. And there's an EAL4 plus evaluation underway. The higher levels, like 5, 6, and 7, are really quite difficult, and they'll be very difficult to do for an open source system. But the point here is that SE Linux has the right security mechanism. And because of those economic arguments, you have to grab what you got, and you have to move forward, or you're not going to improve the security at all. So what is type enforcement? This is the whole reason we're going with SE Linux. It's because it has this mechanism. If there was another high assurance operating system that had this mechanism, it could be a very viable approach too. It's the mechanism that's really interesting here. So type enforcement is a mandatory policy, which means that the system designer sets a security policy when they build the system. It's not up to the system administrator, and it's not up to the end users. This is a very important point, which I'll get to later. Unlike some other mandatory policies, it's very flexible and is very granular. I can control what kind of signals you can send to another process running in a different domain. So that kind of control gives you a lot of power for enforcing security policies. The other advantage of type enforcement is it fits reality. If you look at the Bell-LaPadula model, which is a breakthrough model, and it's your classic military model of an unclassified level and a confidential level and a secret level and a top secret level, and the relationships, if I'm at top secret, what data can I see, what data can't I see? It matches what you'd expect. And there's some breakthroughs in there, like in the star property and what have you, about not having the ability to write data down. If you're a top secret and you can read top secret data, you can't write unclassified information, because a Trojan horse running at a top secret could then take top secret information and, unbeknownst to you, encode it in unclassified information. Now, that was a huge breakthrough. But the problem with this sort of strict hierarchical model is it doesn't fit a lot of real-world cases. Even in military environments, obviously they have this unclassified, secret, top-secret hierarchy, but they have real-world applications where type enforcement fits much better. The granularity and flexibility of type enforcement comes at a cost, though. You have to configure it, and you have to get it right, or you really haven't bought anything. So, when the Bell-LaPadula model, you have this nice mathematical statement of the policy. That's great. You know what you're going to do. Maybe it doesn't fit reality, but you know what you've got there. With type enforcement, you have to set it up to make it correct. So in type enforcement, in a nutshell, basically there's a resource. It's a file, a socket, a process, there's a bunch of other things, but it's basically a resource.